Thank you very much for the introduction, and thanks to the organizers for putting together this very nice conference in this beautiful place. And thank you also for giving me an opportunity to tell you about our recent developments in the studies of hard rods, and specifically in the kind of a quantum version of the hard rods gas. So the classical one, I guess you're all familiar with, but we'll talk about the quantum version. And the kind of main idea that I would like to communicate is that we could think about the quantum hard rods as really the simplest model that captures some essential complexity of quantum gases in 1D. So this is work done with Stanisław Kiedrzyński from our university and Emilia Witkowska from the Polish Academy of Science. The first part of the work was done with them, and then in the other part, in the second part, I collaborated with Oleksandr Gamayun from London Institute of Mathematical Science. Let me start with a short motivation. Why would we be interested in studying quantum hard rods? So one reason is that, of course, the classical hard rods are a kind of paradigmatic model that helped us understand dynamics, hydrodynamics in low dimensions to great extent, right? Also kind of reaching the kind of mathematical proofs. So we are missing this on the quantum part. Now, this is maybe more personal motivation, is that so when I was learning about the quantum integrability, I had found all these great results, especially concerning algebraic beta ansatz, quantum inverse scattering method, etc. And they're all great. And then you kind of arrive at certain formulas, which are almost something that you can extract physics from, but quite not. Okay. So we kind of quite short. We kind of stop quite short from actually extracting physical information from this very kind of extraordinary methods. So so part of the motivation is kind of to look at the situation where we can do a bit better. Now the third motivation is I think it's great for teaching quantum and body physics. So this is, teaching is one thing, but another, I just want to kind of highlight the importance of toy models. So I really think that this quantum hard rods is a perfect toy model for teaching many-body quantum physics. One reason, for example, is that you don't really need second quantization. So everything that I will tell you about today is just plain wave function physics, okay? We don't need anything sophisticated, as you will see. And there are some suggestions for possible experimental realization of the quantum hard rods with Rydberg atoms. So that would be, of course, great, and this also puts a certain motivation to study them. Okay, so what's the gas of hard rods? Yeah, we are all familiar with this. So we have a number of particles. They move in 1D, and they have certain length A, and they cannot overlap. So the Hamiltonian classical or quantum contains the kind of kinetic energy part and the hard rod potential, which is either 0 or infinity. Now, for the sake of establishing the conventions, I will use n for number of hard rods, L for the length of the system. There will be density rho 0 appearing frequently. And if you think about the physics of this system, there's one important parameter, but kind of packed in different ways. So one way of thinking about this is the free length, which is the kind of the length that we give to the system minus the length that the particles occupy, and we can rephrase this as a packing factor. So if you can consider this combination rho 0 times A, and this packing factor can vary from 0 to 1. Now, as we all know, this gas of hard rods, especially the classical version of it, attract a lot of attention, spanning over, almost now 100 years, let's say, or even earlier, starting with some van der Waals gas. So now important for my talk today are the results for the correlation functions in the classical hard rods. So this especially the result of Flicker from '68. And then on the quantum side, there was also some progress. Kind of more sparse. So the wave function was written in 40s, then the equation of state by Sutherland in '71, and there were various studies of correlation functions with Monte Carlo methods in the last 2 decades, let's say. So what's kind of, if we kind of start comparing classical and quantum, so the first thing that's missing here are some analytical results for correlation function, and that's where we would like to fill in. That's the gap that we would like to fill in. So maybe something more about the physics. So if you look at the classical hard rods, so the thermodynamics is very simple.
Sorry, one question. I mean, when you talk quantum, I mean, you mean both Fermi and Bose?
Yes. Yeah. So for the observable, for the correlation function that I'll be considering, the statistic doesn't matter. So if you look at the thermodynamics, essentially the hard rods gas, the classical one are just free particles with excluded volume. Okay, so the only physical effect of the hard rod's length is the effect of the excluded volume, and the same thing happens in the quantum version. So this is the volume of the gas at pressure P and T is the volume of a free fermionic gas with the correction that you have to account for the finite size of the particle. Okay. Now, so what we would like to understand, so you could say that, well, because of this excluded volume principle that we see at the thermodynamics, both at the classical and quantum level, this quantum hard rod gas is simple. Okay. So I would like to argue, and I will show you actually a proof that it's not true. So this simplicity at the thermodynamic level doesn't translate to a simplicity at the level of dynamics. So I mentioned this result of Flicker from 68. So this is the correlation function, density correlation function. So we ask, if there is a particle at 0, what's the probability or what's the correlation to have another particle at certain distances? And this, as a function of the hard rod's length, you see there's some kind of ridge behavior. So essentially, when the rods or this packing factor increases, we see the kind of quasi-crystallization in the system, because essentially particles have no space to move. So on the quantum side, we don't know what is this. And I put here 2 question marks. So one is, okay, to get some formula for the correlation function. And the other smaller question mark is to really understand the physical, kind of physical reasons why we get what we get here. Physical reasons that underlie the result here. And my main message is that the effect of the correlation function is not just this excluded volume. Okay, so there's much more. So as I said, I will be interested in this kind of 2-body density correlation function. So this sometimes is called dynamic structure factor. And the methods that we will use are kind of typical to integrable models. So we use resolution of the identity, we use Heisenberg equation of motion to get to a spectral representation or a Fourier transform of it. So the ingredients to compute this correlation function are essentially 3. So we need to understand eigenstate, we need to understand the form factors, and we need to perform this spectral sum over the eigenstates. Okay, so this is a program that was have been tried in many different integrable models with different kind of techniques on getting the form factors or performing the spectral sum, etc. But to the best of my knowledge, it was never kind of fully accomplished in an interacting theory. Okay, so what I will show you today is that in the quantum hard rods we can really fully accomplish it. Also fulfilling the kind of premise of quantum integrable models. So one of the premises, at least, of the quantum integrable models is that essentially all eigenstates are equal, in the sense that we don't have to look for some effective methods that, I don't know, maybe look at thermal state, ground state physics, etc., etc. So we can really perform this, we can really compute this dynamic structure in any eigenstate of the theory. Okay, so let's try to kind of go through this shopping list. So we first need to understand the eigenstate. So we have this Hamiltonian hard rods potential, and we are interested in the eigenvalue problem. As Benjamin was showing 2 days ago, there is this very nice transformation in hard rod system from the kind of physical coordinates to hard rod coordinates, which essentially shrinks down the particles to point-like particles. And in this new coordinates, the Hamiltonian is a Hamiltonian of free particles with the exclusion principle, which mimics, kind of Pauli principle. So if we use that, we will find the the wave function. So of course, the wave function of free fermions is a Slater determinant. So if you go back to the real coordinates, we will just kind of blow up the space between particles, and we will find that the only kind of effect of finite length of the particles is this shift here in the positions, which depends on the particle that we are looking at. And this works equally well for fermions or for bosons. We have to symmetrize this wave function, so I kind of symmetrize by taking the absolute value of it more subtle. Yes, yeah. That's so we can, of course, then kind of symmetrize over all the orderings and things like this. The usual beta ansatz technique. So now from this free fermion solution, we get the momentum and energy, which are, as we expect in a Galilean invariant theory, if we think about this Kj as momenta, quasi-momenta, rapidities. Now this form of the wave function takes, it's a Slater determinant, but you can really represent it in the more familiar form to the integrable community in terms of the beta ansatz form. So it's a simple exercise for two particles. You can expand it, and then you can find the scattering matrix, which is the scattering matrix of the now of the quantum hard rods. I will say a few more things about it in a second. So now, well, we've kind of followed the typical path. So once we have wave functions, we put the system in a box and we quantize it. So we get the beta equations. Now, because the wave function, sorry, the phase shift, which is written, so maybe I should write it here, it's linear in momenta. The beta equations become extraordinarily simple and can be solved. So these are the beta equations for the. So now I'm working, so this is a very good point. So the crucial, it's actually the crucial thing that we are now imposing the periodic boundary condition on the real system, okay, not on the constructed one. So I'm trying to be consistent. So when I use R, this is the real, these are real coordinates, and X are these hard rods coordinates. Right, so the beta equations can be solved. So this is in a way, kind of as simple as it gets, because we have explicit expression for the quasi-momenta, and essentially, there is effect of the excluded volume in this that we put here, this free volume, but there is also a shift, or kind of backflow, back reaction, how you want to call it, from all the particles present. Now, so at least initially, I would be interested in the ground state physics. So the ground state is, as usual, formed by, kind of filling in the Fermi sea. So we have Pauli exclusion principle. Everything works like in, say, in the Liebig-Linear. And then we have also, if we look at the low energy states, we can look at the basic excitation. So if you're familiar with this canonical paper by Lieb and Liniger, actually this is the second paper by Lieb. Everything works like there. So we have a ground state. We can create a simple excitations which are particle. If we take a particle from the Fermi edge somewhere else, there is a Hall mode. If we take a particle from within the Fermi sea to the edge, and there are Umklapp excitations. If we take particle from one side to the other, we get a nice dispersion relation for this prototypical excitations. And here, because the beta equations are solvable, we have solution, we can really get explicit expression for the dispersion lines. So it's much simpler in the Lieb-Liniger. And we also find that, well, there are sound modes at small momenta. So the quantum hard rods should fall within the universality class of the Lattinger liquid, which was known before. So the Lattinger parameter also takes a very simple form. It's in terms of this packing factor. Now, let me tell you just a few more things about the structure of the eigenstates. So the beta equations are like this, which means that there is this shift to the, say, pre-fermionic quantization by the momentum. And then it means that there are some special cases. So when we look at the state which has zero momentum, there is no shift. Okay? Therefore, the ground state of the theory takes the same form as in the free fermionic case. Okay? And this similarly, so if you think about equilibrium, this also holds for equilibrium. So if I take a thermal equilibrium state, I assume that a kind of average over states with zero momentum, I will see only free fermions in excluded volume. Okay, and that's what we see at the level of thermodynamics. Now, but if we look at the states at finite momentum, then there is this shift. So there is a backflow, and so if I create an excitation, so I change one of the quantum numbers, all the other quantum numbers are slightly shifted. Okay, due to this back reaction. Now, there are, among all those states, there are some kind of special, or you can look for special states. So you can imagine that this combination AP is proportional to 2 pi integer, okay? And then this will be then an integer, or could be understood this as modifying the quantum number. And there we are again kind of on the regular lattice of the momenta as in the free fermionic theory, just slightly shifted. Okay, so those states are kind of special, and it's an interesting question whether they kind of appear in dynamic response and if they're important or not. So we are trying to answer this question, but we are not yet there. Okay. So the next ingredient on the list were form factors or matrix elements. So let's move there. Right, so we are interested in the form factor of the density operator, and kind of taking the glory of integrable models, we consider K and Q here to be arbitrary eigenstates. So as I said, no second quantization, no algebraic beta ansatz, nothing like this is needed. So I'm really kind of doing quantum mechanics of wave functions. So I will compute this going to the wave function representation of states, etc. So some simple manipulations, and we get an explicit representation of this in terms of the wave functions. Okay. So so now, well, unlike in the other models, we can actually compute this integral. So I think I have some time also to show you a bit the computations. So of course, the reason is I don't want to go into the details of the computation, but I would like you to kind of understand what are the important ingredients for the computations, and because they matter for the physics. Okay, so we are asked to compute this multidimensional integral. So here R is parameterizes n positions. So that we have this wave function, which is also an n-dimensional, and it takes a form of this slightly shifted, slightly determinant. So the steps are the following. So first we go to the Hard-Roth coordinates. So we again kind of shrink the system. So we can do this because wave function is 0 where otherwise the Hard-Roths would overlap. Then I know this Slater determinant, so I can expand it, and I get everything in terms of some basic integrals. Those integrals I can evaluate, and here in the evaluation of these integrals, because they involve momenta, the periodic boundary conditions are important, the quantization rules are important, okay? And that's where these shifts will appear. So they appear here, there's this shift. So this shift here is really brings all the complexity that we will see in a second, okay? So the integrals can be evaluated, and we find some expression in terms of sum over 2 permutations. So the 2 permutations come from expanding both of the Slater determinants that are here. Then we work out a bit the combinatorics, and we can reduce it to a single permutation. And when we have a single permutation, there is a hope that we can write it as a determinant. And this happens, and we get the Cauchy determinant expression. So this is my final result for the form factor, which is, I will later compare it with the form factor in Lieb-Liniger model. But the essential ingredient of this is there is a Cauchy determinant, and of course, we know a lot about the Cauchy determinant, so we can capitalize on this. Anyway, the main message here is, no algebraic beta ansatz needed. Okay, so let's now look a bit. Yes. It linearly depends. Yes. Yeah, but then So this is, of course, important for thermodynamics, because then if you think about the kernel, it's constant and you can do everything, but here it's...
I'm sorry. Oh, the same computation fails in generic case because matrix or scatter shift depends on case, so you cannot factorize out.
Yes.
Thank you.
So let's look a bit at this, form factors. So now what I would like to, on the next slide, which I will reveal in a second, what I would like to kind of prove is that the complexity of the hard rods, the complexity of the hard rods is much more like the complexity of the Lieb-Liniger model rather than the free fermions. So in order to do this, I will make a kind of an experiment. I will take I will kind of randomly draw two eigenstates and I will check what's their form factor. Okay. In free theories, we expect that the form factors essentially are either 1 or 0, because either you kind of look at, so you look at the form factor with some operator between. Now, if you're in a free theory, this operator either creates another eigenstate or doesn't create another eigenstate. Okay? So that's why it's either 0 essentially or 1. Whereas for example, in Lieb-Liniger or in quantum hard rods, we see really a kind of a continuum of values, which means that if I randomly choose two eigenstates, the form factor will generically be non-zero. Okay? And this is essentially the reason of complexity of evaluating the spectral sum, because I have to sum over a lot of eigenstates. Okay? In free theory, I understand that there is just a finite number of eigenstate or finite class of eigenstate contributing. Here, I have essentially kind of everything contributing. So this is my numerical proof that quantum hard rods are interesting, because they're not like a free theory, they're like Lieb-Liniger. Okay. Now, to say more about this, we can look at the so-called X-ray singularities or Anderson orthogonality catastrophe. Namely, this is to ask a question, how does form factors scale with the system size? Okay. So this is a bit technical, but so at this level, I can maybe only just say that they should, so essentially they should scale like number of excitations plus possibly some correction. So this correction in free theory is 0 for the form factors that we are considering. So the form factors scale just with the number of excitation, which is, if you kind of think about the spectral sum, this is what you need to have a finite correlation function. Whereas in interacting theories, there is the fractional power law appearing here. So this C is non-zero. So I can just take this form factor. I can look at certain excitations. I will look either at the whole excitation when I take a particle from within to the edge, or particle form factor when I take a particle from the edge and put it somewhere else. Okay? And with this formula, I can just evaluate this form factor for different system sizes. And I see that if my theory is free, so this is Lattinger parameter equals 1, so A equals 0, then I get a nice linear scaling with M equals 2. Whereas if I crank up rho 0 times A or decrease K, I see that the form factors start to scale with fractional power law. And this fractional power law that we get is essentially different for particle form factors and whole form factors. So the whole form factors, in a way, kind of start to diverge. So they scale slower than we would expect, whereas the particle form factors scale faster and they vanish. And so this is in agreement with kind of generic predictions of the nonlinear Lattinger liquid for k smaller than 1, and we are in this regime. This is just kind of maybe for a bit for an expert, but this is another proof that we have a non-trivial theory. Okay, so let me now kind of to conclude it, compare it also with Lieb-Liniger at the level of the formulas. So, well, Hamiltonians, phase shifts, pseudo energy, so some thermodynamic beta ansatz thing. So here we get an integral equation that we still have to solve. In this case, we just get some renormalization of the chemical potential. So you see the complexity is, slightly increasing comparing the two. And I think this kind of gets really seen at the level of form factors. So this is the form factor of the density operator. We could zoom in to see the details, but I think it's it's clear that it's much more complicated than just the Cauchy determinant. Okay. So they agree. So of course, I mean, if you think about 1 over C to be small, and you keep the leading order, yes. Yeah. Yeah, but then, so if you do like this deformed Tonge-Girardot gas, you really believe that 1 over C is small. So you keep only the leading corrections. Okay, so here, A for us is not small. So they agree only perturbatively for small a or for large C. There is a lever when they overlap. Yeah, so we are in the attractive, well, depending how we think about this. So from the Lieb-Liniger point of view, we are in the attractive regime, which is for fermionic theory, it's repulsive regime, right? So Lieb-Liniger for Latinger liquid is an attractive interaction. Yeah, I don't know, but I think the formulas are analytic, so it can be, yeah. Mm-hmm. Mm-hmm. Wow. Give me a lattice. I don't know. No, so I mean, yeah, I think it's an interesting question, but kind of for me personally, I don't want to go to the lattice because if I have lattice, we have other methods to solve. I really want to focus on continuum where we lack numerical methods to tackle these problems.
Yeah, so related to Alvise, but you answered already. So how do I simulate this? So because numerically.
Yeah, so I don't want to simulate this. I want to solve it.
Okay.
Well, it's an yeah. Right. So let's do the correlation function. So there is a way to compute something with the computer. So we can use the abacus algorithm by Jean-Sébastien Coe, which was designed to perform this kind of spectral sums. So the assumption is that we know all the ingredients to this formula. And then the question then is how to efficiently perform the sum, okay? So we are in continuum, so Hilbert space is essentially infinite, exponentially large. So one has to kind of understand what are the important contributions to the sum in order to be able to evaluate this correlation function in a finite time. So the abacus algorithm is a kind of heuristics that allows us to do that. Now, we don't have to kind of be blind because there are some relations that we know that the correlation function should obey, so we can check this relation. So essentially, we go over the Hilbert space, and from time to time, we check whether how well this F-sum rule is satisfied. And if we are satisfied with the way it's satisfied, then we stop the computations, okay? So here I'm showing you plots so this is this dynamic structure factor. So you see the kind of its shape reminds of this elementary excitations that we started with for different value of the Latinger liquid parameter. So again, I'm kind of switching from the Hard-Roth's length to the Latinger liquid parameter. So K close to 1 are free fermions, and the minimal value of K that we can reach for the kind of physical theory is K equals 0. So here we essentially try to span this interval between 1 and 0. So at at K close to 1, we essentially get free fermionic physics. But then things start to change. So at this, we see the kind of appearance of a second umklapp, and there's the kind of second continuum of excitation that's clearly visible. And this goes on to a smaller value of K even more visibly. So here we have system sizes at which are particle numbers. So for me, always system length and particle number are equal. that we can do. So here we can do moderately large system sizes, but as k approaches 1, we are really restricted to much smaller system sizes, and this is the reason for all this kind of finite size details that we see here.
Do you see the...
Yes, yeah. Well, I can, at the very end, I have a plot with edge singularities. So one thing that we can, that this numerics also teaches us is that, if you consider, if you look at how many excitations we need to get reasonable saturation of the sum rule, we see that this number increases drastically as we decrease k. So for k equal close to fermion, we need something like 10 to 8 for 64 particles, but for 16 particles and much smaller k, we need like 10 to the 10 power or something. So we are essentially killed, and it's very difficult to explore with this approach the most interesting regime of strong interactions. Okay? So that's why we turn to analytics. I think I have. So that's already kind of a prelude to the analytics. So one thing that we can do is, so as I said, at 0 temperature, we expect Lattinger liquid physics, and Lattinger liquid has a prediction for this. So here I'm looking just at the equal time correlation function, which is in terms of this harmonic series with the prefactors. So these prefactors are non-universal. They depend on the microscopic details of the theory. And many years ago, we were kind of looking at the relations between these prefactors and the form factors of the microscopic form factors. So there is certain prescription that allows us to relate this prefactor to certain form factor. I don't want to go into the details here, but now we know these form factors, so we can just compute these prefactors and therefore establish essentially the Lattinger liquid prediction for the quantum hard rods. So these prefactors have some nice features. So they're plotted here, and you see that from time to time they kind of, so this is logarithmic scale. So from time to time they kind of vanish. So this vanishing of this form factor is related to this TG-alike behavior of some of the excitations that I was mentioning. So let me just quickly. So it's this. They vanish from time to time because of this behavior. I mean, I can explain this better, but for now, I think that's enough. So for this quantum hard rods, we can compute this prefactor. It's kind of relatively simple formula involving some Berns G functions. And one thing that we can try to now do is to address this small k limit by just evaluating the Lattinger liquid prediction in this case. And what we see essentially is, so if you look at these prefactors, they all kind of converge to the single value here, which if you then think about this, it means that all the momenta modes start to essentially contribute equally to this correlation function. And then if you think about Fourier transform, if you have this kind of regular contribution, we get in the real space something that has peaks. Okay? And these peaks are essentially show the crystallization or small Lattinger liquid parameters. Now, so that was kind of analytics, but for an effective theory, but in fact we can do much better. So we can compute really this, we can really evaluate the spectral sum for any eigenstate k. So here k is fixed, we sum over q's, and the form factor is given by this expression. So this result relies on an earlier result. So the complexity of this problem essentially follows from the fact that if you recall the beta equations, we had this shifts, okay? And these shifts depend on the state that you're looking at. So this is what complicates the sum, because if this nu was independent of the momentum, so if we assume that it's independent, then there is actually an expression for this sum. Okay? It takes a form of some Fredholm determinant with certain kernel, which is of this form, and these functions E plus, E minus are known. I'm not giving them here because they don't fit. So you see, essentially, so this is this sum is a kind of appears in some free fermionic problems. So if you think about this new parameter here, this is like a twisted boundary condition or something of that sort. So we can perform certain computations for free fermions with twisted boundary conditions. So that's the kind of physical origin of this problem. What's important for us is that this really works for any eigenstate K. So in the final result, we have this Fredholm determinant in which the distribution of particles in the state K enters. Okay, so it could be ground state, could be finite temperature, could be whatever you want. So now the only problem that we had was kind of how to use this result for the case where nu is actually dependent on the state that we are looking at. So the idea is actually very simple. We can kind of use a filtering, or maybe in other words, we can kind of try to compute it for whatever shift, and then we keep only the shifts, the contributions from shifts which agree with this formula. Okay, this is a kind of, you compute more, and then you kind of erase what you don't want. So because we compute more, in a way we kind of go over all possible shifts. There are additional integrals appearing in our problem. So here the formula was expressed through a single determinant. Now we have more complex structure because there is like double integral, and this d nu here is a single Fredholm determinant. Okay, so the complexity is much larger. And then the kernel has the same form with these functions are explicitly given. Okay, so I would like to really kind of highlight. So this is an exact result for the correlation function for any x and t and the Hartrud's length in the thermodynamic limit for any eigenstate in which you want to compute the correlation function. Now, this is complicated, but it's exact. So, there's if you put some effort, you can try to work on it. So we are putting this effort. So I think we got this formula like a couple of weeks ago. So we are still struggling to understand all its consequences. But let me tell you about a few of them. So things simplify if you look at the static correlator. So we still have all those integrals, but the determinant gets simpler and it takes a form of a sine kernel, which is again well studied. So here is the plot of the static correlator. So this is the kind of a proof that this formula can be evaluated. So we have the results for the static correlator. So there's a bunch of results here. So let's go slowly. So there is t equals 0 result, which is kind of invisible. It's here. There's this red thing that goes up and down widely. And this agree with the dashed line, which is also kind of visible, which is the Lattinger liquid prediction. So in a way, we have a confirmation of the Lattinger liquid theory. Okay, this is at this stage it's numerical, but we actually have a proof that or we could think about a mathematical proof of the Lattinger liquid form of the correlation function. Now, if we crank up temperature, what we expect is that the correlation will decay and the oscillations are less visible, and we can crank it up to the t infinity even limit when we get some results. So this t infinity limit I will talk about in a second. Okay, so that's for the static correlator and kind of plots. Now we can try to understand a bit the structure of this formula. So now things become kind of complex, but we can do some further rewriting to get a form which is, I think, quite illustrative. Because then now the contribution to the static correlators comes from finite number of contributions, okay? And these contributions can be understood in the following way, that if I look at the correlation at certain distance, okay, there's a certain number of particles that I can fit into this distance, okay? So the contribution is essentially from, I look at this distance and within this interval, I have one particle, I have two particles, but I can't have too many particles. So this n max tells me that there is finite number of contributions, and this can be understood as contributions from having 1, 2, etc. particles in this interval. And at t equal to 0, this expression is equal to some data from random matrix theory. the probability density of the distance of an eigenvalue to its n+1 neighbor. So this relation is just an observation. There's probably a way to understand it. We are not yet there. So the other result that I want to mention is the infinite temperature limit. So at infinite temperature limit, this function p becomes a simple exponent, becomes a simple function, and it actually matches now this flicker result from 68. So we recover these classical correlations at infinite temperatures. You can ask me a question why it's at infinite temperatures, and I will answer. But for now, I will show you a summary. So, exact expression for the density form factor, exact thermodynamic, matches Latinger liquid. We recover the classical results. There is some relation to the random matrix theory that I would like to understand. And from a more general perspective, I kind of try to claim that this is the simplest non-free model of a quantum gas. And all the complexities are due to the equations. There are two effects. There is excluded volume, which you see in the thermodynamics, but there is something that you don't see in the thermodynamics, is this dynamic quantization, A times P. And yeah, many open possibilities. So we are working on some of them. And so this talk is also, if you like the quantum hadrons, I invite you to try to work together, because I'm extremely excited about this. So I would like to share the excitement. Thank you very much.
Thank you very much. Any questions?
Thank you very much, Miłosz. I really enjoyed the talk. It's very exciting. I have a very natural question. You didn't need the whole machine of beta answers and so on. Okay, so there's the holy grail of beta answers, also computing overlaps to doing auto equilibrium. Do you think that in this model you can do something?
Yes, we are computing them right now. Yes, I think it's possible.
Do you still need the pair structure that you need for the integrable states or not?
It for sure simplifies a lot. So we are starting there, but
that would be quite interesting, because it could have states that you can get exact solution that have completely different structure than what we have now.
Yeah, it's an open question for now. Yes.
Okay. Thank you so much.
So I have one. Well, I don't know. Okay, so I have one question. I mean, did you ever try to look, let's say, at momentum correlation functions? So you would see the difference between bosons and fermions. And
yes. So that's some work here.
Oh, okay.
Yeah. I mean, we looked a bit.
Work in progress.
Yeah, I mean, we look a bit, and essentially you get a bit what you would expect. So for fermions, it's kind of simpler, and for bosons, it's much more complicated. And starting with the Lennard formula for the pre-theory. I mean, from Girardot.
You promised to show the H exponents. Thank you. Does it fit the kind of exact expressions from the Latinger?
Yeah, so we have to check this. So numeric. So this is numeric. So numerically, it's hard to get the exponents. Now,
but you can plot them.
I would dream that from this formula you can get H exponents, but this is like miles away.
But they come from the scattering shifts. So
yes, so this
and I don't know dispersion relations. So you can track it and just being powered.
Yes. So this is I agree. This is a simple check that we could do. We haven't done it yet. Yes. Mm-hmm.
So Miłosz, yeah.
Mm-hmm.
Hi. So thanks for the nice talk. It was really interesting and nice. So since you have access to all the eigenstates and you can compute essentially all form factors, have you thought about looking at the statistics? Because you mentioned the paper of Fabian Essler, but you also did it for the spin chain, and it seems that the statistics is quite universal and robust.
Yeah. No, I think this is something that also can be easily done, because it's much easier than Winiger computationally, and maybe we could learn about. So in the Fabian's paper, I think they have some kind of guesses for what's the statistics of the form factors. Maybe in this case, we could actually find the distribution.
Yeah, in particular, there is, I mean, they find some Frechet
This
distributions.
kind of relates to this, but that's not exactly the same picture.
Yeah, they find some Frechet distributions, and for the spin chains, we find a Gumbel distribution, so,
Okay.
but it's similar. But then there is a funny log corrections they have. So maybe this model allows to clarify whether the log is really there or not.
Yeah, excuse me. Yeah, thank you for your talk. This connection that you found with RMT, I mean, so can you just say it or show it again? So this is, so in which limit is that exactly? So that's the...
I think it's the probability density that we have. So that's in the bulk of the distribution of the eigenvalue. So if I have an eigenvalue here, and then I look at the distance x, how many that I have exactly n eigenvalues inside this interval. I think it's this one.
But S of x, I mean, this is obtained in the limit of, so this is the stationary, this is the large time limit, right?
No, this is, sorry, so this is t equals 0.
Okay,
equal time.
Okay.
Yeah.
And so this happens then, I mean, because you have already the sine kernel before, right? So I guess you obtain this as a...
Yeah. So the fact that we get the sine kernel for equal time correlators.
That actually gives rise to that.
Yeah.
Maybe this is the same question, but it didn't look like the RMT mapping depended on A other than through n max, right? So it seems like it might be an A equals 0 property that's...
Yeah, so I don't quite remember the formula, but it might be that essentially the A dependence enters only through this rescaling here, and inside P there is no A dependence.
Yeah,
it's just T equals 0. It might explain this. Yeah,
I'm just remembering that when you get Wigner-Dyson, you can do it with a free fermions in imaginary time, which seems similar. Thank you.
Any other question?
Can I go? Do we still have time? Oh, okay, maybe a comment about the A negative. So I think if you, so I mean, okay, this is great. But you agree that this is basically, I mean, the genius idea is to take C negative and then large C, right?
No.
No?
No.
But okay,
so
what I want to say is
this
that,
is not perturbative in A.
No, fine. But I mean, what I want to say is that here you are in the regime. I mean, linear it would be like in the attractive regime, right?
Yeah, not integer larger than 1.
Yeah. So to access the repulsive one, you would need to change the sign of A.
Yeah.
But then I'm afraid that then you would change the scattering when you have a negative A, change the order of the particles, and then probably you lose the Slater determinant structure. I think. I don't know. What do you think?
I think it's an open question what happens, but yeah. So maybe on a kind of related note, I think it would be nice to try to understand this, I mean, whether we can understand this correlation function as some kind of, I don't know, like following the TT bar deformation of the free fermions.